Section 4.2 is all area. There's a lot of geometry in this. It should be fairly easy. Yeah, I know, then I've cursed everybody. There are 4 different ways that we need to look at this, which will be a little confusing, but I'll go slow and we'll move through it together. So first, our objectives. We're going to talk about the concept of area. So we have a relationship. You'll recall when we talked about derivatives, we defined a derivative as being 3 things. What are they?
Slope of a tangent.
Slope of the tangent line.
Position. A limit. Or a value.
Well, he's clearly not using our
I have them all written down.
It is the slope of the tangent line. 33%. Yes, sir. Rate of change. 66.7%.
You're rounding up.
And velocity. Very good. 100%. Area is the big thing for limits. Limits. Now you got me. For integrals, which we'll get to in a second. So we're going to approximate the area. We start with some approximations because we don't have enough tools right now to get an exact area. And again, this will make sense in a little bit. So we're going to do some approximations. We are going to use some limits. And then hopefully you've been practicing drawing your squiggly thing so it doesn't look silly.
Mine just looks like an S still.
Just still looks like an S? Stretch it out a little bit.
Then it takes up more than one line.
Sometimes
I have college.
All right, so here we go. So
I get it.
in a couple weeks, months, I mean, when I ask you that same question, like what are the 3 things that derivative stands for, and you rattle off a rate of change of velocity and the slope of the tangent line, I'm also going to ask you? I was going to ask you, what does the integral represent? And your answer for that is the area under the curve. So you might want to write that down, area under the curve. And we're going to start by taking some approximations, and that's why this initial stuff is just geometry, because we're going to be finding the area of rectangles.
So is area of a curve, could you repeat that?
Area under a curve
Is the integral?
is the integral,
Integral.
also known as the antiderivative. Okay, which is what I just said. Okay, so it's the area under the curve. So here's a curve. Let's talk about the function first, that red line. What can you tell me about that function? Could possibly be, but we don't know that for sure.
It's not linear.
It's not linear, excellent. It's not a badger.
Concave up. Increasing. No, it's, wait.
Yes.
It was
Yeah.
really hard for me not to repeat what you just said in the way you just said it, because it was pretty funny.
You can repeat it if you want to.
Concave up. It is concave up. And what else?
I thought you said that.
Increasing.
And it's increasing. Okay, those are the 2 things we want to look at. My example to start is a function that's concave up and increasing. Our pictures will change depending on the shape of the curve. Remember, we've got 4 possibilities. Increasing concave up, increasing concave down, decreasing concave up, decreasing concave down. And the pictures will look differently. And like I said, we don't have the tools yet to find the exact area under the curve. Eventually, we're going to be able to find, drop a line down from this point here and calculate that exact area, regardless of what shape the function is. But for now, we just have to approximate, so I'm using rectangles. Why rectangles? Because that's how we start. How can we make the area more accurate? Because you'll see I've got a bunch of wasted space here, right? See all those white areas? So it's not going to be
Shaded.
just shaded in. Okay, so color it purple.
We're gonna count it.
Oh my gosh.
You got a genius over here.
This might take longer than I thought.
I'm kidding.
Eric,
You could make a lot of rectangles.
increase the number of rectangles. I like it. Any other ideas?
Try.
Dan?
Just coloring different ones.
Could use triangles for those. Or, for those of you that were good in geometry, what happens when you combine a rectangle with a triangle?
Trapezoids.
Trapezoids, correct. So we will eventually look at these as trapezoids, which would combine the idea of a triangle with a rectangle. But for now, we're going to do rectangles.
I'm sorry, guys.
Okay? Okay, so these are 5 rectangles.
What about the little, when you You'd have a curve, so then you couldn't fit the trapezoid. There's a little bit of space.
What is the?
Correct, it's not perfect.
Oh.
Yeah, the trapezoid isn't the perfect solution. The calculus that we learn later will be the perfect solution. We're still doing approximations.
Oh.
Okay, so notice I've got 5 rectangles that go from 0 to 10. How wide is each one?
2.
2. Very good. How'd you get that, Max?
I'm just that smart. You just look at
This
one-
coming from the guy that suggested we just color them purple.
Okay. Well, you could just look at the graph, or it's just 5 times 2 is 10.
No, see, but if you tell me you got that by doing 5 times
I
2,
didn't
you're
do that.
using
I
the
looked at the
answer to
graph.
get the problem that you, how did you get 2?
I just looked at the graph.
Just looked at the graph. You just saw that that one starts at 2.
And then then you keep going, that's 4, that's 6.
Okay, what if I broke it into 5, or sorry, there are 5. What if I broke it into 10 rectangles? How wide would each one be?
It's just madness.
It will be one.
It's still
That's the answer.
Yeah.
Just be madness.
It would just be madness, correct.
No, you-
How wide would they be?
One.
1. So what if I broke it into 20 rectangles? How wide would each one be? Half. How are you doing that calculation?
Divided by however many rectangles.
Oh, okay, so we.
Excellent. Wow.
Recording this?
Yes. You can save it for prosperity's sake. Okay, so the starting point is A, the ending point is B. N is the number of rectangles. The width of each of those rectangles is delta x.
Did you say start points A and then?
Starting point's A, ending point is B. So to find the width of each rectangle, you take starting minus ending, ending minus starting divided by the number of rectangles you want. Which, even though Max doesn't realize it, that's the calculation he did. 10 minus 0 divided by 5, correct?
Right.
Is 2.
Yes.
Good. Initially, we're going to keep all these rectangles the same width because it'll make your life a little bit easier. However, the answer will be less accurate. So we start with something really absurd with these big fat rectangles with a bunch of wasted space that we could color in purple. And we will change some things later on. One of the things we'll change is we'll shrink the width of the rectangles. I'll show you that in a second. We'll also change the shape. And we'll also change the width of individual rectangles because you'll see that it'll work better if you have different shaped rectangles, but that comes in the future. Okay. So you'll notice I've got these 5 rectangles, same picture, but each rectangle hits the graph in one of the corners. This one, or in fact all 5 of them, hit in the upper left-hand corner. These are called left-hand rectangles. So what you do when you draw these rectangles is you find out what your delta x is, you mark off all those regions, you draw lines up to the graph, and then you decide, am I going to use a left-hand rectangle, which means where it hits on the left, you come across, or am I going to use a right-hand rectangle, which hits on the right and comes across? Okay, and I'll show you some examples of this in a second.
Wait, can you repeat what you just said? I didn't follow that.
The left-hand rectangles are rectangles whose upper left-hand corner touches the function. See, upper left-hand, upper left-hand, upper left-hand, upper left-hand, upper left-hand. So it makes sense if we have left-hand rectangles, we would also have right-hand rectangles. Those come in a second.
Oh. That's weird.
Okay, so here's a little bit different function. You'll notice now that as I have right-hand rectangles here, if I flip it over here, I've got left-hand rectangles. So as I slide this over, notice the amount of white space under the curve shrinks until we get a very large number, and then it pretty much looks like the area under the curve. So we can go with something as an that was a weird noise. Something that's an absurd approximation because I have a ton of space there, to something that is more accurate. Okay, now let's look over here. Notice these are all left-hand rectangles, right? Or not bad English. These are all left-hand rectangles, correct? Are these left-hand rectangles?
Yes.
Yeah, they are. Notice it still hits on the left-hand side. But over here, those left-hand rectangles are below the curve. Over here, the left-hand rectangles are above the curve. The right-hand side is what's called an underestimate. The left-hand side is what's called an overestimate. Why? Max?
It's overshoots the graph.
This one does.
Yes.
And this one is an underestimate because it's below the actual area. Okay, so the question is, where do you have wasted space? On the right-hand side, we've got wasted space between the rectangles and the curve. On the left-hand side, we've got wasted space between the curve and the rectangle. And you see then, by changing the shape of the curve, I purposely moved this curve over a little bit more so you can see in this region it's decreasing concave up, and now we have part of the rectangles above it. And then if I flip this to the other side, I get right-hand rectangles. Now let me shrink that a little bit. Where they go up and they hit the right-hand side of the curve and then come across. Okay, and I'll work you through an example here to show you what it looks like and how you solve the problem, but I wanted to show you what happens when you increase the number of rectangles to a very large quantity. So what we want to do is we actually want to find the area of those rectangles. That's all you're doing on homework tonight. And there's no tricks. It's just literally calculating the area of a bunch of rectangles. So if I want to find the area of this rectangle, I know how wide it is because we did that calculation already. It's delta x. How tall is it? Well, the height of this rectangle is that distance right there. What is that distance? That distance is the y value at 8, also known as f of 8. If I move over one rectangle, it has the same width of 2, because we did that calculation already, which is over here out in front. How tall is it? It's f of 6. So again, you're looking at the point where the rectangle hits the function, and then using that to find the area of the rectangle. Find the area of all 5 rectangles, add them up, you're done. And there's no trick to it. That's it. That's all we're going to be doing. Okay, so there's our right-hand rectangles. Things are different now if I pick this starting one. In the left-hand rectangles, I used it over here on the left-hand side. For the right-hand side, I use it over here, so that's f of 10 for the height of that one. This is f of 8, f of 6, f of 4, f of 2. Don't use f of 0 because it's not relevant for this problem. Okay, so let's see what this excuse me. Let's see what this looks like from the start. So I've got a function x, 1/2 x squared plus 2. And I'm going to work with the interval from 1 to 4. Using 3 rectangles. So if I'm going from 1 to 4 with 3 rectangles, how wide is each rectangle?
1.
So delta x is equal to 4 minus 1 divided by 3, which is 1. We'll start this one nice and easy. Starting at 1, I'm doing another one at 2, another one at 3, and another one, wait, 1, 2, yeah, there we go, up to 4. Okay, so I start with that. Then I have to decide which one am I going to use. I'll start with left-hand endpoints. So I start with my first rectangle here. I'll call that Roman numeral 1. This is Roman numeral 2. This is Roman numeral 3. The plan here is I'm going to find the area of each of those 3 rectangles and add them up, and I'll be done. Go up the left-hand side of this rectangle. When I hit the curve, I come across. Go up the left-hand side of this rectangle, hit the curve, come across. Go up the left-hand side of that rectangle, come across. Everybody with me so far? Yes. No. Yes?
Yeah.
Good. So I'm going to find the area of 1, 2, and 3. So let's start with number 1. What's the area of rectangle number 1? How wide is it?
1.
1. How tall is it? How do I find how tall that is? Well, I went 1, 2, and 3. How do I find f of 1?
Plug 1 into the function we're given.
Plug 1 into the function. So I get 1/2 plus 2 is 5/2. Any problems there? Okay, what's the area of 2? Same width. And 2 I found by doing f of 2. So f of 2 would be 4. And then the area of region 3, 1 times f of 3. And what's f of 3? 9/2 plus 2, 13/2. Do that right?
Yeah.
Okay, so the answer to the question then would be the area under the curve is approximated as 18 times
26 times 13.
13. That's supposed to be a 3. Okay, before we move on, is anybody confused? What do you got?
Yes, so you found area 1 by multiplying 1 by plugging 1 back into the original equation, correct?
Correct.
And
So
then
this,
you
hold
just
on,
see
before
this
you ask
here?
your question, this is the same thing as 1 times f of 1. This was 1 times f of 2. This is
Okay.
1 times f of 3.
Why is it's 1 because delta x is 1?
This one or that one?
That
This one?
Yeah.
Yeah, because delta x is 1.
Oh, so
Because
that's
the area of
whatever-
this rectangle is delta x times the height.
So that's whatever delta x is, so it could be like 3 or.
Could be whatever you want,
Okay.
yeah. We good? Good.
Do we need units?
No, it's not crucial in this point. If you're feeling saucy, you could just write unit squared. All right, we good before I erase?
Well, the
I don't
area
know
is
if
just.
you're-
Oh, go ahead, go ahead.
why don't we do this?
Oh, you said go ahead at the same time now? Who goes?
Gianna just took the lead.
Jumped right out in front. Go ahead.
Sorry. Do you wanna go?
Like, serious.
Ninja
Okay.
Hunter Bear.
Oh, when you
Ninja
add
Hunter
them
Bear.
to
Ninja
Oh, why?
Hunter
You
Bear.
had the lead.
Ninja
Why
Hunter
did you-
Bear.
Why did you give
Ninja
up the
Hunter
lead?
Bear.
You
Here we go.
You
Ninja
called
Hunter
it.
Bear.
Ninja
Do
Hunter
them
Bear.
Mr. Cake
Because you
Bear.
called it
Ninja Hunter
Bear.
What?
Bear.
Ninja
Ninja
Hunter
Hunter
Bear. I'm not kidding.
Ninja Hunter
I'm
Bear.
kidding. Do it.
Ninja Hunter
It's
Bear.
fun. I'm not making a
Ninja Hunter
noise.
Bear.
Do it.
Do
I'm
it.
giving Nikki.
Alright, she's giving it away, she's a ninja.
Okay, thank you. For the area.
She did ninja the lead from her, so I wouldn't mess with it.
For the area, because in the first example, you multiplied something by 2 when you added it?
Yeah, because delta x was 2.
Oh, okay. Oh, okay.
Oh, so you multiply it by.
Yeah, that 1 is delta x.
But like for the final thing, when you're adding it all together, you still have to multiply by delta x.
What do you got?
Why didn't you do? Oh, just kidding. It's never mind.
Okay.
Sorry.
Anything else? All right, let's do the right hand now.
Don't you have to say it's the? I changed my mind. The area is approximately 13 in the interval from 1 to 4. Don't you just talk about the interval or no?
You could. It's implied in the problem, so
Okay.
you know it's not as persnickety as when we were doing like first derivative test where you have to write out the sentence in a certain
So
format.
you just add them all together.
Just add them up. That's like I said. That's all we're doing. Literally, is finding the area of rectangles. A-time.
So you add them up and then you multiply by delta.
No, I've already multiplied it by delta x. That's what the one is.
Okay. I'm just.
You just do it.
Real.
Maybe this won't be as easy.
All right. Same problem. Now we'll use right hand rectangles. So we're still going 1, 2, and 3. Up here, up here, up here, up here, 4. This is the rectangle I want. I go up the right hand side, I hit the curve, I come over. Come up the right hand side, hit the curve, come over. Come up here, hit the curve, come over. Now notice it. Go ahead, Libby.
Do you have to say if it's like an underestimate or an overestimate?
Great question. I was just going to ask that. In the problem we just finished, was my answer of 13 an underestimate or an overestimate? Underestimate, because the value was below the curve. This one will be what?
Over.
Overestimate.
So
Okay,
do you
so
have to like say that in your answer though?
only if it asks you.
Okay.
Yeah, and they will ask you. They'll ask you to approximate the area, and then the secondary question will be, is it an underestimate or an overestimate? Okay, so this is, we'll call this alpha, beta, and gamma. Area alpha will be 1, which is delta x times f of 2. The area of beta will be 1 times f of 3. And the area of gamma will be 1 times f of 4. Because notice we're on the other side of the rectangles now. We did f of 2 already, didn't we? 1 times, was it 4? 2 is 4 is half, yeah, that's 4. F of 3 was 9 halves, 13 halves. And then f of 4 is 16, 8, 10. So therefore the final answer is 14 is 28, 38, 41 halves.
Yes.
Eric.
So, if you have an overestimate and an underestimate, couldn't you take like the average to get a answer that's closer to what we actually get or no?
That method will get you closer
It won't get you
to the accurate answer, but not necessarily, because it depends on the shape of the curve. Very steep curve might generate more error in the overestimate than in the underestimate. Dan,
So if there's a problem just like this in the homework, do you have to do both of them or can you just pick one?
follow the directions. Sometimes
So
it'll say
it'll
do a
say-
left and a right, sometimes it'll just say do left or just right.
So it'll always say do
Yeah.
which. Alright.
Okay? We good so far?
Oh, yeah.
What's the matter?
You can also-
Do you still have the other one? Or did you erase it?
I erased it. Alright, good? Alright. I think the next couple of slides just take you through the solutions. Yeah, so there's delta x. You can do it, notice in the way I did it here is I took delta x and multiplied it by the height of each of those. In hindsight, I think it makes more sense to do the area of each individual rectangle and then add them all up, John.
So for the left hand, you did 1, 2, and 3, but then for the right hand, you did 2, 3, and 4.
Correct.
So for attached that.
Correct. And that will depend, that's not always the case, but in this case it is because it's increasing concave up.
At some point it would be less work to do it that way.
Correct. Yeah, if you got a whole bunch of nasty rectangles. Okay, so then we did that already, 20, is that what we had?
Yeah.
Yeah, okay, good.
Yeah.
All right, upper and lower sums. So we talked about this already, but now we're gonna vary this a little bit. So we've done left hand and right hand limits. What we're gonna look at is something now called circumscribed, and I can't think of the other one. Come on, Reedy. Inscribed, thank you. Inscribed, it probably says up there somewhere. Yeah, there you go. Inscribed and circumscribed. Inscribed means always below, circumscribed means always above. So you've got 4 possibilities now. Left and right, we did already. Inscribed, notice this curve changes. And what you end up doing is when you draw your lines up there to get all those different rectangles, you have to decide, are you gonna go left or are you gonna go right to keep it below the curve? Okay, so notice that all of these are below the curve, even though the shape of the curve changes. If I did this as a left hand or right hand rectangle, I'd have some above and some below. This will always be an underestimate. The inscribed rectangles will always give you an underestimate. On the far right, I've got circumscribed rectangles. They are always above. So in direct opposite to this, when I draw all my segments up to the curve, I decide if I'm going to go left or right to keep it above the curve. And they give you some fancy terminology here. S of n is the inscribed answer. Capital S of n is the circumscribed answer. And that the actual area, like Eric said, is somewhere between those two values. Finding the average won't always give it to you, but it would get you closer to that actual answer. Does that make sense? Okay, so 4 possibilities. Left hand and right hand, showed you how to do that. Inscribed and circumscribed. And like I said, with inscribed and circumscribed, you follow the same procedure. You're just finding the area of rectangles, except when you come up to the curve, you have to decide, am I going to come from the right side or am I going to come from the left side? Question?
So if you take the average of both, what would that give?
Not always.
Oh,
It'll get you closer, but not the exact answer.
okay.
Okay? So there's, looking at a curve similar to the one we just did, there's the way that you would do that. Okay, the inscribed is an underestimate because there's area below the curve and the rectangles, and the circumscribed is above because you've got area between the rectangles and the curve. And they'll look different if we take a different graph. If we look at a graph that's concave up, decreasing, you're going to get some different rectangles, and that's why drawing an accurate graph is going to be helpful. Okay? Because it'll just help you visualize where those rectangles are, how wide they are, that kind of thing. Okay, we're all done. So again, don't make this more difficult than it has to be. Draw a careful picture of the graph in the interval that you're using, figure out what delta x is, and do some geometry. Okay. Calculate the area of rectangles over and over again, add them up.
Even if you're doing, so like the right hand rectangle, you say one above the curve. approximately.
Yes. These are just approximates right now, so, yeah, overestimates, underestimates will determine, will be determined by whether it's above or below.
Are we, or do we have to, when we were calculating the inscribed and circumscribed,